Hey guys, I want to work a few examples with you, get you set up and ready to work some homework problems. Closer look at testing. Several ideas come up in this section dealing with null and alternative hypotheses, type 1 and type 2 errors, multiple testing, practical versus statistical significance. It's quite a variety of topics. Certainly multiple testing and publication bias figure prominently in here. But let's take a look at this question. BPA in tomato soup. A consumer protection agency is testing a sample of cans of tomato soup from a company. If they find evidence that the average level of the chemical bisphenol A, BPA, in tomato soup from this company is greater than 100 ppb, they will recall all the soup and sue the company. So let's first state the null and alternative hypotheses. So let's see, this is a test for a single mean. So the hypotheses are H naught. Let's go for a different color here. Let's try a dark blue. Maybe this one. Alright, well that's going to be kind of bright maybe, but that's alright. I needs bright. H naught mu equals 100 versus the alternative mu is greater than 100, right? So where mu represents the average level of the chemical bisphenol, all right, so this is in tomato soup from this company. That would be our definition of what we're talking about for our mu. So we're going to use sample data to investigate that. All right, now what does a type 1 error mean in this situation? So let's just think about it. What it means is that under the null hypothesis, that the null hypothesis was true, and we rejected it. So in this case, it would be that the bisphenol, our BPA level for the soup was actually 100, and we concluded that it was more. So let's say a type 1 error means that the company's mean is within normal bounds of 100. That is, the null hypothesis is true. Let's see, null hypothesis is true. But the sample obtained happens to show, and we might add incorrectly, that the mean is too high, and the agency ends up recalling the soup and suing the company when it shouldn't have. So that's a pretty serious consequence. But we may think that that's worth it for the safety of consumers. On the other hand, what would a type 2 error mean? It would mean that the company's really being irresponsible. Well, let's just say that that consumers are perhaps endangered by the high levels of BPA, but our test is not sensitive enough to pick that up. All right. So I filled in a response for that. A type 2 error means that the company's mean is too high, the mean level of BPA. The null hypothesis is actually false, but the sample obtained doesn't give enough evidence to show that it's too high. And the agency incorrectly decides not to recall the soup or sue the company. So which is more serious, a type 1 or type 2 error? There's no right answer, I suppose. But the thing is, they both seem pretty serious, but I guess from the benefits of the consumer, I would say. So let's see. I would probably say, from my perspective, for the consumer, type 2 would be a more serious error, right? Because that would mean it's possibly unsafe, and we conclude that it is safe. Now, actually, my first job for my first career out of undergraduate was market research, and I worked a few years for an ad agency, for Wrigley's Chewing Gums ad agency, and did market research for them. But after that, I worked for Kraft Foods, and we had food safety issues that came up. In fact, while I was working there, they had an incident with Listeria monocytogenes in some of the frozen bars, like Klondike bars. These were called Polar bars at the time, made by Kraft, and it was so serious, and some pregnant mothers had consumed them, and so there were deaths involved. And so, we certainly the company tried to be very careful in such matters, and so they certainly don't want to make mistakes either. But we still might think that the stakes are different in the sense that the company still has a profit incentive working sort of against the safety considerations. All right. Just reminded me, I hadn't really thought of that in quite a while. Here's a story from July 1986 in Chicago Tribune. I remember going into the office that 4th of July weekend and having a discussion with the security guard about this. This was when they started recalling, and the brand never recovered in that case, and so they just discontinued the product, if I recall correctly. All right, now, so that's actually the serious issue, right? Public health and how to use statistics in a positive way. And now, in this case, this is a hypothesis tested similar to the way our legal system works. For each underlined word or phrase, give the analogy in a statistical test. And if you've watched the interactive lesson, you should be familiar with this because this comes up here, there as well. But it's a good thing to have in mind when you're thinking about this. So a person is innocent until proven guilty. So innocent would be our null hypothesis, and the alternative is proven guilty. Evidence must be beyond a shadow of a doubt. So this would be the data that's collected. And you might even say it's, say, like an X bar or a P hat. It's the statistic. Beyond a shadow of a doubt, well, that's a level of significance. Type 2 error probability, so that would be our alpha, perhaps, the significance level. There are two kinds of errors: convicting an innocent person or releasing a guilty person. So which is which? Well, this would be a type 1 error, and is thought by society to be the more serious error, right? We assume innocent unless proven guilty, and so that's because we would want to avoid, at least that is the consensus, convicting an innocent person. The type 2 error would be releasing a guilty person, so the person was guilty, but we failed to reject the null hypothesis. All right. So I find that that's useful to kind of internalize this, because it helps you make sense of what we're doing in statistics and how it parallels these ideas. All right, so vitamin E and heart attacks. Example 3, suppose 100 tests are conducted to determine whether taking vitamin E increases one's chance of having a heart attack. Suppose also that vitamin E has absolutely no effect on one's likelihood of having a heart attack. The test will use a 5% significance level. So how many of the tests are likely to show significance just by chance? Well, it's a 5% test, so it means that if the null hypothesis is true, 5% of the time we're going to get extreme results. Extreme enough to reject the null hypothesis. So we would say 5% of 100. So how many would be 5? Should be significant just due to chance. If only the significant tests are reported, what is the only information the public is likely to hear? Well, they're likely to hear that vitamin E increases, to determine whether it increases one's chance of having a vitamin, having a vitamin. Yes, so they would only hear the news that vitamin E increases your chance of having a heart attack, and that would not be supported by the data in general. In fact, it might look something like this, right? So we'd probably get out the large print, and we'd say vitamin E causes heart attacks in all caps, maybe. Even though that was just one of the sort of the errors, the type 1 errors. So this is the issue with publication bias. We have to be careful about the studies, and we want to look for a pattern of evidence. There's discussion of reproducibility of results in this section. And that's a big reason why I want you to learn R in this class, because it makes it easy to hand over your work, your analysis, your data, to share it publicly and let others see what you've done and try to replicate your results. Without that, we risk having this sort of publication bias undermine the validity of research. All right, experimenting with sample size on stat key. Suppose that we are testing on a coin to see if it is fair. All right, I'm sorry. Yes, we have done this already together. So I lost sight of that I had done that in the activity. But if you didn't do it already, go ahead and give that a try. 560 out of 100 tosses, or 56 out of 100 tosses, and 560 out of 1,000. But actually, let's go ahead. I'm going to go ahead and do that, get the p-value for just these two, and we'll compare these and see what conclusions we can draw. All right. Actually, I was double checking the activities. We didn't do exactly these calculations, so let's go ahead and take a look. This was 56 out of 100, so 56 out of 100. And then we're going to generate a bunch of these, maybe do this about 5 times, 5,000. Look in the right-hand tail. Is that what we're testing? Oh, sorry, we're testing a two-sided alternative hypothesis. So we'll be looking in the right-hand, let's see, how do we want to do this? We could use the two-tail in this case. The lesson that I gave you when I was talking about this, I did something slightly different with the right-hand tail and doubling it. But in this case, because we don't know whether these will have symmetric tails, I think I'll go ahead and use this two-tail approach. And just to make sure that we get all the results here, I'm going to take 0.59. And over here we get 0.41. So we pick these up and we get a total p-value of 0.09. So p is equal to 0.09 here. And what we're looking at here then is, now if we increase the sample size, see, this is p hat is equal to 56 over 100. And here p hat is equal to 560 over 1,000. So we might say it's the same effect size, 0.5 versus 0.56, right, in each case. But the question is, which one gives more evidence, stronger evidence? Well, this is a much larger sample, so if we're concerned about this big of a difference, and we probably would be with a coin, so let's see what we would get for our data here, for our results here. So 560 out of 1,000, and we do that, simulate that experiment many times. That's a lot of coin tossing, I hope you can see, right? We're tossing a coin 1,000 times and repeating that experiment 5,000 times. So do the math, that's a whole lot, right? Okay, so two-tailed, and we want to get the proportion outside of what we observed, which was 560. So I'll say 0.559, just to make sure to include that. And so that's going to be very extreme, 0.0002, and we double that to get 0.0004. So by this... So this is much smaller. So why are the p-values so different? Well, we're seeing the role of the sample size in influencing this. So the difference is due to the sample size. The larger the sample, the more precise we get. We're better able to detect the difference. We're less likely to make a type 2 error. Because under the alternative that it's unfair, we're less likely to incorrectly conclude that it's fair. All right, so but what's driving this is the role of the sample size. All right, so thanks for working through these with me, and thanks for listening, and take care. Good luck on the exercises on them. And as always, reach out if you run into any difficulties.